As we're getting going, I want to draw your attention to the objectives. So today we're going to be describing the relationship between frequency and wavelength. So look out for those two words and the connection between them. You had a little bit of an intro to that yesterday during the worksheet portion of your flame test. Then we're going to talk about why certain frequencies of light excite specific atoms. And lastly, we're going to start talking about Bohr's model of hydrogen, but if the previous class is any indication, we won't get all the way through that today. Okay? Let's launch right in. So, we have a model of the atom, Rutherford's model, okay? But it was incomplete. It did not give us a full understanding. We knew now that it wasn't like the plum pudding model, but we didn't really know what was happening with the electrons. We didn't know, one, why the negative electrons weren't drawn in towards the positive nucleus. Because remember, positives and negatives are attracted to each other because they're opposite charges. So there wasn't a full understanding of why don't the electrons just stick to the outside of the nucleus? How can they be moving around there and not be attracted to the nucleus? And we didn't fully understand even how those electrons were distributed. We now knew that they weren't distributed evenly like a plum pudding, but we didn't really understand how they were actually distributed. In order to understand the new model and how we arrived at the new model, we have to first understand how light moves. An understanding of the movement of light will help give insights into that. So that's where we're going to start today. Okay? It's important to understand that light has properties of both particles and waves. So sometimes it can be described as moving like a wave, and sometimes it can be described as moving like a particle. And which description you use, sometimes it's more helpful to understand a situation if you describe light as a particle or if you describe it as a wave. So it depends on the situation. Visible light, so the light that we see around us, is part of the electromagnetic spectrum. That's all of the types of electromagnetic radiation. If you don't know what electromagnetic radiation is, it is a type of energy that exhibits wave-like behavior and it travels through space. There are 7 types: radio waves, microwaves, infrared waves, visible light waves, ultraviolet waves, X-rays, and gamma rays. You interact most commonly with visible light, but the other ones are in fact involved in your life, maybe in ways that you don't know. All of these electromagnetic radiation travel at 3.0 times 10 to the 8th meters per second. We call that the speed of light. And in a vacuum, it is constant, so it's always this speed. If light has to travel through a substance, like through glass or through air, it travels just slightly slower, but it's still very close to that constant. And when we represent it in an equation, we represent it with the letter c, like a lowercase c, as the speed of light. The motion of waves is repetitive and continuous and can be described with 2 measurable properties. So when we're talking about waves, think about waves in water, right? You're not going to have a wave and then a break in that wave and then that same wave continuing, right? It's continuous and it's repetitive. The motion is up and down, over and over again, right? And the 2 properties that we use to describe the motion of waves are wavelength. Okay? This is the distance between corresponding points on adjacent waves. So if we draw it like we would a water wave, right? We have this up and down motion of water waves. A wavelength is going to be from one point on the wave to the same point on the next one. So that could be the top of the wave, it could be the bottom of the wave, it could even be a random spot along the side of the wave. As long as you make it the same spot both times, that's still a wavelength. We represent wavelengths when we are using them in an equation with the Greek symbol lambda, which just looks like an upside down y, basically. And we measure them using the unit for distance. So for larger waves, we might use meters. For smaller ones, we could even go as small as nanometers. The second property we use is frequency. Frequency is the number of waves that pass a given point in a specific time. Usually the time we use for this is how many waves pass in 1 second. So if we wanted to kind of do a drawing representation of this, if we had that water wave, we would pick a point, like say the leg of a pier, and say how many waves pass that point in 1 second. So we'd be watching and counting how many crests or how many troughs passed in that time. Well, how many specific wavelengths, so from crest to crest and trough to trough. Okay? And that would be our frequency. We represent frequency with the Greek symbol nu, which looks like a slightly squiggly V, or more commonly with an F because it's easier than trying to draw that V and differentiate it from other V's that we use. So your book uses nu, so I wanted to introduce you to it in case you're looking through your book, but I'm going to use F here in class. And frequency is expressed in waves per second. So sometimes you will see it labeled with S to the -1, and sometimes you'll see it labeled with hertz. That's the same unit. Okay? We're talking about waves per second. So hertz is a number of waves per second. 1 hertz would be 1 wave per second. If we go back to that drawing I made, right? So we have, nope, go back to the drawing. I want to draw. Okay? If I want more waves to go past this point in the same amount of time, what do I need to do to the wavelength of the wave? If I want more of them to be able to go past it. Yeah, I need to make the wavelength shorter. So that gets us to the relationship between wavelength and frequency, which is that they are inversely proportional. That means as you increase the frequency, so if you increase the number of waves going past a point in 1 second, you have to decrease the wavelength. You have to make it smaller. Okay? Mathematically, we can relate these two to the speed of light in the following equation. The speed of light, which we described on the previous slide, is equal to the wavelength times the frequency. And for light, that's a constant speed. Let's take a second to check our understanding of this. So I'm going to set a timer. I'm going to do more than 30 seconds because you need a little more time to write. You're going to write down characteristics of wave motion, so what is wave motion like, and then you're going to write down how frequency and wavelength are related. And then after 30 seconds are up, I'm going to ask you to share one thing you wrote with your partner. So again, it'll be more than 30 seconds, probably more like a minute. Okay, so back here, we had a good description of wave motion. How did you describe it?
Continuous, there's no breakage, like between, just keeps on going.
Yeah, continuous, there's no breakage, it's always going. And you said what else?
Repetitive. So
repetitive. Yeah, it's repetitive. It's happening the same way over and over. And then we had over here a really good explanation of frequency related to wavelength.
The higher the frequency, the shorter the wavelength.
Yes, higher frequency, shorter wavelength. They're inversely proportional, if we remember from the first chapter. Good. Okay, so we are going to move on then and start talking about particle motion. As we've now talked about wave motion, we know light moves as a wave sometimes, but sometimes it moves more like a particle. And a really good example of this is something called the photoelectric effect. So, the photoelectric effect is what happens when you shine light, so like a beam of light, on a metal, and it causes that metal to emit electrons, so to give off electrons. Okay? When scientists first started observing the photoelectric effect, they noticed that there was a minimum frequency required by each metal in order for electrons to be emitted, and it was different for each metal. So some metals required lower frequencies and some required higher, but there was a minimum, and if you didn't meet that minimum, then electrons weren't emitted by the metal. They were also not emitted continuously. So it wasn't like a continuous stream of electrons coming out. It was more like they were coming out as a packet. Okay? And Max Planck called these packets that were being emitted quanta, which is just the plural for quantum. A quantum of energy is the minimum amount of energy that can be gained or lost by an atom. So he noticed there's a minimum amount of energy that you can put in, and then that energy will come back out and be lost by that atom. But there's this minimum amount, and it doesn't come out as a continuous stream, it comes out as a packet. This was very confusing to scientists to begin with, because if you remember, at this point in time, we are thinking about light as behaving only like a wave. So they were like, well, if we're putting a continuous amount of energy in the form of a wave, why aren't we getting continuous out? It didn't make sense to them. So Planck proposes this idea of these quanta that are packets that are being emitted, and he also proposes a way to calculate the energy emitted in a quanta. Okay? He suggests the following equation for the energy of a quantum. The energy, E, of the quantum is Planck's constant, a numerical constant that he came up with, which is 6.626 times 10 to the negative 34th joules per second. Joules is a unit of energy. Okay? Times the frequency of the light that is emitted. So he was saying if you take the constant that I've come up with times the frequency of the light emitted by this atom, then you will find the energy of that specific quantum. Pause there for it. So at this point, everybody's like, okay, well, that's all well and good. We can calculate the energy of these packets that are coming off of this, but we still don't understand why it's packets and not a wave coming out. They're just very confused. And so, in 1905, a man named Albert Einstein proposed what at the time was considered to be kind of a wacky idea. He said, what if electromagnetic radiation can behave as both a wave and a particle? At the time it was a wacky idea, now we recognize it to be the best explanation for how light behaves. Okay? He said light could have lots of wave-like properties. It could have a frequency, it could have a wavelength, but what if sometimes it can also be thought of as a stream of particles? What if we think about it as a stream of particles? And so then if you're adding a stream of particles to something, it's possible that just particles could come out of that as well. And he called these particles photons. A photon is a particle of electromagnetic radiation that has no mass, and it has exactly a quantum of energy. So, for different atoms, photons will have different energies. And because he was relating photons to quantums, he proposed that the energy carried by the photon could be calculated using Planck's equation. Energy of a photon is equal to the constant that Planck proposed and the frequency of the light being emitted. So, how does this help explain the photoelectric effect? Well, electromagnetic radiation is going to be absorbed by matter in whole numbers of photons. So it's not going to absorb a partial photon. When you shine light on metal, it's going to absorb one photon or two photons or three photons of energy, it's not going to absorb 1.5 whole numbers of photons coming in. Okay? And electrons will only be ejected from the metal surface if you strike them with enough energy to dislodge them. Sorry. You can think about this as like a fairgrounds. Okay? How many of you have been to the fair and seen the game where they ask you to knock the cans down with the ball? Right. If you threw a continuous stream of ping pong balls at those cans, are they coming down? Probably not, right? They make those carnival games difficult, right? Even with the normal ball that they give you, you're probably going to have a hard time knocking them all down. So let alone with a ping pong ball, right? It doesn't matter how many ping pong balls you throw at it or how continuously you throw them. The ping pong balls just simply do not have enough energy to knock the cans over. But if I gave you a softball, you would probably be able to knock the cans down. That's the same thing that's happening during the photoelectric effect. So remember, they were surprised that that there needed to be a specific frequency of light in order to emit electrons. The reason for that is that each atom holds on to their electrons with a different level of tightness. Okay? So some atoms, it's really difficult to knock an electron loose, and for some, it's less difficult. So for an atom that's difficult to knock electrons out of, you have to have light with enough energy to knock that electron loose. So any frequency underneath that level is not going to knock an electron loose. It doesn't matter how much of that or how continuously that light hits it, it doesn't have enough energy. But if you do reach the level of energy required, then you will knock an electron loose. And that level is going to be different for different atoms because they hold on to their electrons differently. So, checking for understanding. Again, we're going to jot some stuff down. This time I want you to tell me what is the photoelectric effect and how do we explain why that's happening. Who can tell me what the photoelectric effect is? Go ahead.
So the electromagnetic radiation, it absorbs a certain number of the photons, but it will only absorb them in whole numbers.
Okay.
And so then electrons will stay attached, and a certain amount of force is needed, or energy, I should say, to remove them.
Great. Yeah, so we have matter, right? It has electrons, and if you shine light at it, sometimes you can cause electrons to be emitted. That's the photoelectric effect, basically. It's absorbing these energy in photons, and sometimes it emits energy. But it will only do that if there's enough energy to knock an electron loose. So we just reviewed the why certain atoms are excited by only certain frequencies, and we talked about the relationship between frequency and wavelength. So tomorrow we'll hit the last objective, which is to discuss Bohr's model of the atom, where we'll kind of tie all this information we've been learning together in a nice bow. Okay?